AFGC Center. It was nominated by Dr. Vivien from Texas Tech, and he's Cody Zilverberg, PhD student, and he'll be sharing with us a presentation on fossil fuel use and associated carbon emissions.
Forwards, backwards, and then the pointers in the center.
Okay, thank you. All right. Thank you for the introduction, and thank you for the opportunity to participate here. First off, I'd like to recognize my co-authors because this was a large project that required a lot of people and was far beyond what I could have done by myself. To appreciate our research, I think that you have to understand the setting where it took place, and that's the Texas High Plains. Now, historically, this was a shortgrass prairie grazed by native herbivores like the bison you see here. We only get about 19 inches of rainfall on average, but that's very erratic from one year to the next. More recently, of course, a lot of this land has been converted to cropland, to annual crops like cotton. We produce about 30% of the cotton in the U.S. now. Also, rather than the domestic herbivores, we have a lot of cattle and feedlots. In fact, we have about 30% of the cattle on feed in the U.S. are right in the Texas High Plains. But a problem that we have here, especially with the row crop agriculture, is water use. What this slide shows is in the red areas, well, this shows us the Ogallala Aquifer. And in the red areas, those are places within the aquifer where it's projected that 20 years from now, we won't have enough water to operate a center pivot. And so clearly that shows that we need to start thinking about doing some things differently because our irrigated agriculture, at least, depends on water from this aquifer. Another issue that we face in the Texas High Plains and that really is faced throughout the United States in agriculture is energy and carbon. And at the farm level, we see that fuel and fertilizer costs are a big concern. On more of a sustainability and global level, when we rely on fossil fuels, we know this is a non-renewable resource. So there's some concern there. We don't know when it will run out, but we know that there's a limited amount. And finally, of course, we hear a lot these days in the news about carbon dioxide concentration and carbon emissions. And so for all of these reasons, it's, I think, important that we understand how we use fossil fuels and what kind of carbon emissions we have in agriculture. So with these two issues in mind, the issue of water availability and the issue of energy and carbon, we set out to achieve this objective. What we had was we wanted to compare two systems. One system is a cotton monoculture, and that's what we used as our control in the experiment. And the other system is an integrated crop forage livestock system. And so to compare these two systems, we're going to compare them with respect to the 5 criteria you see here: water use, productivity, profitability, impacts on the soil, and finally their energy use and carbon emissions. And of course, the energy and carbon is what I'm here to talk about today. And I want to clarify a little bit about what I mean when I'm talking about energy and carbon. I'm talking about our fossil fuel use, and the carbon that I'm talking about is the carbon that's released when we use fossil fuels. So I'm not talking about carbon that might be sequestered or released from plants and soils themselves. It's just the carbon associated with the fossil fuels. So as I mentioned, we're comparing two systems. On the left, you can see the cotton monoculture. That's our control. We had a wheat cover crop there. This was a 10-year experiment, and after 5 years, that cover crop, we had so much trouble keeping it established that the cover crop was discontinued, but the cotton continued for the full 10 years of the experiment. And the other system is the one that I want to spend most of my time on, and this is the integrated crop livestock system. A little over half of that system was planted to WW Beedall Old World bluestem. This is a warm season bunch grass, perennial grass. And then the rest of the system is divided amongst 2 fields. And these 2 fields were in rotation. The crops that we have in the rotation are listed there. We have rye, followed by wheat. So rye followed by cotton. So the cotton would be no-till planted into the rye. Following the cotton, then we would come to the wheat. And then the next summer, then, we would have a fallow and then finish up going back to rye in the fall. So what ends up happening is, while we have rye in this field, we would have wheat in this field. While we have cotton in this field, fallow in the other field, and then when we get to the fall again, back to wheat here and rye here. Now this entire system was grazed by a set of stocker steers. These were Angus and Angus cross stocker steers, and here's a picture of them here. The way the grazing system worked is that they would come in mid-January, and they would be grazing dormant bluestem. That's what you can see in the foreground of this image. As the rye became available, they would spend a little bit of time on that rye. So maybe one day a week, they'd move over to the rye and then come back to the bluestem. As the rye growth started to speed up a little more, eventually the cattle would be 100% of the time grazing rye. Once they grazed out the rye, then they would move to wheat, which was in the other field. And once they had grazed out the wheat, by that point, the bluestem now had put on its spring growth. So then they could move to the bluestem and graze that new growth until about mid-July. And then they would go to a feedlot. So some of the basics on our system design, as I mentioned, this was a 10-year experiment. We're at an elevation of about 3,300 feet in northeastern Lubbock County. Rainfall is about 19 inches on average. This was a randomized block design with 3 blocks. And for the grazing system, each one of those blocks was about 10 acres, and we'd have 7 or 8 head grazing that entire 10-acre area. So in order to explain how we went about calculating how much energy was used and how much carbon was emitted, I think the best way to do that is to provide an example. So that's what I have here. And to give you a little preview of the results, when I talk about energy and carbon, these terms are almost interchangeable. We found the correlation was so high, it was a 0.99 correlation, that basically when I say one, you can think the other and vice versa. So if we used a lot of fossil fuels, that means we released a lot of carbon to the atmosphere as well. So in this example, I just picked wheat from 2002, and you can see basically what we do is we build a budget a lot like a financial budget, except that instead of putting a price in dollars on every one of the items in the budget, we put a price in megacalories, which is a unit of energy measurement, or in a price in pounds of carbon. And so the first line has planting in it. And so what the planting is going to include, of course, is the diesel fuel that you burn in the tractor. It's also going to include the energy required for the manufacture of that tractor. In the case of a tractor, that's a depreciable asset that you're going to use over many years. So you can take the energy required for its manufacture and divide by its usable life to see how much energy you would charge to the budget in any given year. After planting, you can see we have other things like the seed, fertilizer, some different herbicides, and at the bottom, irrigation and the irrigation system. So the irrigation system, again, that's a depreciable asset similar to the tractor, and so we're going to spread that out over the time of its useful life. And then the other line for irrigation is the power that it actually requires to pump water. And so depending on how much water we use, that's going to be affected in how much energy we use, how much carbon gets emitted. And we add all of these up, and we come down with a number in how much megacalories it took to raise the wheat crop in that particular year. So the results that I will present you now, they're all going to be the 10-year means from this experiment. And what we found was that the cotton monoculture, which is on the left here, used more energy in total than the integrated system. Not only that, we broke it down into different categories, and that's what you see in the different colors here. So you can see that the cotton monoculture also used more energy for irrigation. That's the blue bar at the bottom. So the cotton used more for irrigation than the integrated system. It also used more energy for fertilizer. It used more energy for the mechanical operations and used more energy for the pesticide operations. So in all these different categories, the cotton monoculture used more energy than the integrated system. Also, you can see that most of the energy for both of the systems was used for irrigation. The second most for both systems was the fertilizer. And to put this in terms, rather than megacalories and pounds of carbon, which probably don't mean a lot to people, to put this in something that might make a little more sense, this is a difference of between, say, 2.5 barrels of oil for the cotton system versus 1.8 barrels of oil for the integrated system. But I haven't quite given you the whole story yet, because the integrated system had something that the other system didn't have, and that was these stocker calves. And to be complete, I think we need to include the energy it took to raise those stocker calves. And so that's what you see here in this orange bar. Now, what that is the energy required to basically to maintain the cow herd that produces those stocker calves before they ever got to our experiment. And the assumptions that we made here were that those calves were raised nearby on range pastures, so range pastures in the panhandle of Texas. Now, that's actually a pretty low energy cost scenario compared to some other alternatives. For instance, had we made the assumption that these calves came from eastern Texas where they were raised on well-fertilized Bermuda grass pastures, maybe interseed with some ryegrass, then the energy use would be a lot higher here, and we would see that the integrated system would probably use more energy than the cotton monoculture. Within the integrated system, we had several different forage types, the perennial bluestem, wheat, and rye. And so what I wanted to do is calculate our energy efficiency on each of these different types. So what you see here is how much energy was required to produce one day of grazing, one animal day of grazing on each of these types. You can see wheat was the least efficient, and bluestem and rye were similar. Bluestem was just slightly lower. However, again, I haven't quite given you the whole story yet, because on the bluestem we also harvested grass seed. And so it's probably not quite fair to say that all the energy we used was required for grazing, because surely some of these inputs are also required by the grass seed, and management may have been a little bit different if we didn't have that. So one way to take that energy that we put to bluestem and divide it amongst the two different products is to say, well, how much revenue did each of them bring in, and divide it up proportionately based on the revenue. And so when you do that, what you end up with is, because so much of the revenue came from grass seed, it makes the grazing look much more efficient. And it makes this perennial bluestem look like it was much more efficient in providing grazing days than either the wheat or the rye. So in conclusion, we found that the cotton monoculture used more energy than the integrated system, but that's also very sensitive to our assumptions about where those stocker calves came from, most importantly, how they were raised. I mentioned what if they'd come from East Texas? Well, the reason they would have been required more energy from there is not so much because of the transportation. The transportation from East Texas to West Texas would be very little compared to the energy it took to maintain that cow herd. It's the energy to maintain the cow herd that was the big energy use there. Also, the biggest carbon and energy expenses for both of these systems were the fertilizer and the irrigation, and then for the integrated system, of course, we also had the big energy cost of the stocker calves. And looking to the future, how might we improve our efficiency of energy use in agriculture? Well, here's several different options. One would be to improve the nitrogen and water use efficiency of our crops. A second option might be to use more perennials as opposed to annuals for our forages, although, as you saw in those previous couple slides, that's an area that could really use some more research to determine just how much more efficient they are, and if that's a robust thing that would stay between landscapes and different forage types. And finally, because the stockers use so much energy, improving our cow-calf efficiency that produces the stockers we need would be another way to reduce the energy use here. And so to wrap up, I would just like to acknowledge the sources of funding for this research and some of the sources where I found some of the images in this presentation. Are there any questions?
For the crops produced, whether it was cotton or livestock, did you look at dollars returned for the megacalorie expended?
The question is for the crops or the livestock, did we look at dollars returned for the megajoules expended? We did complete financial budgets for these systems as well. We didn't relate it directly to the megajoules expended, but I think I could do that because Because over 10 years, what we found was that the profitability of the two systems was almost identical. And so because of that, since the cotton system used more energy than the other system, I would have to say that it had a poorer efficiency. Again, that's going to be subject to the same assumptions about those stocker calves, and so that could easily go the other direction as well.
Any other questions?
Would you
Yes, sir.
consider meat goats as an alternative to stocker cows?
Meat goats is beyond my area of expertise. I certainly would say it would be worth a try, but in terms of their energy efficiency, I couldn't make a comparison. Sorry.
Do you take into account water use efficiency of the cotton versus the integrated system, and how much water efficiency you have and how it would affect the results?
The question is, did we take into account the water use efficiency of the two systems and how it would affect the results? In total, the cotton system used about 15.5 inches of water per year versus just under 12 inches for the other system. So the cotton system used more water. Now, in terms of comparing their efficiency, I guess, with respect to what output, it's a little bit difficult to compare the output from a cotton system to the output from a stocker system because we have cotton lint versus, live weight gain on our steers. So we would have to have some measure where we could measure if, how much energy per or how much water per unit of what output